we do this a lot. We say, let's, because it's easy to visualize, we'll have a conductive rails. And we'll put a sliding conductive bar here. Okay, you see what I'm doing? I now have a circuit that I can change the area of the circuit very easily by sliding the bar to the left or the right. And if this whole thing is sitting in a magnetic field, all we care about is what the magnetic field is doing inside the loop. We don't care what's happening to the magnetic field outside the loop. Inside the loop, there's a magnetic field into the page. So the first thing we can do is look at forces. If we slide this conductive bar, which way? How about to the right? We slide that bar to the right. So that bar now has some velocity to the right. That bar is a conductor. It has charges in it, right? Electrons free to move. So a charge moving to the right in a magnetic field, if it was a positive charge that was free to move, it would feel a force in which direction? Positive charge would go up. A negative charge down, right? And what direction is current flow? Flow of positive charges. So the current would flow in that direction, right? We move this bar to the right, positive charges would start going up and around and up and around. And as long as we keep it moving, we generate this flow of positive charges in the counterclockwise direction, or this flow of negative charges in the clockwise direction. But either way, we call that current in the counterclockwise direction. So that's using sort of forces. So we get this counterclockwise current. Okay, another way to look at it is with something new we're going to learn today, Lenz's law. And then we'll talk about Faraday's law. Lenz's law is conceptual. It tells us the direction, but it doesn't tell us about the magnitude of the induced EMF. Faraday's law tells us about the magnitude of the induced EMF. It also tells us the direction, but you have to be very, very careful with the signs and knowing how to assign positive direction to flux and negative direction and positive direction to change of flux, and it becomes a little complicated. What I do, I use Lenz's law to determine the direction and Faraday's law to determine the magnitude. All right, so Lenz's law tells us that when there's a changing magnetic flux, we will get an induced current in the loop of wire. So remember, there's no current initially. All we have is a bar crossing the conductor here. There's no current, right? There's no battery, nothing. We move the bar to the right. So what happens initially, there's a change in flux because the area got bigger, right? That's one way we can change the flux. You get a bigger fishing net, right? So we're making the area bigger. So the magnetic flux increased into the board. As we move this to the right, we have more and more flux into the board because the area is getting bigger. So Lenz's law says that a current gets induced that creates its own magnetic field that counteracts the change that created it. It always opposes the change that created it. So if we move this bar to the right, we now have more flux into the page. So a current is going to get set up that creates a magnetic field out of the page to counteract that increase in flux. So it's going to go counterclockwise like I've drawn there. So it always opposes the change that created it. And the reason for that is conservation of energy, right? We know that we don't get something for free. So let's pretend for a minute that the induced current, let's pretend for a minute we push this thing to the right. And when we push it to the right, a current gets set up that adds to the flux instead of opposes the flux. So we push it to the right a little bit, and we have an increased flux into the board. If an increased flux into the board created a current that increased the flux into the board, then as soon as that current gets created, it adds to the flux into the board, which creates more current, which adds to the flux into the board, which creates more current. We'd have no energy crisis, right? We'd have free energy. All we have to do is give this thing a little push, and as soon as it starts to create current, that current would create more current, would create more current. We'd have all the energy we ever needed. And we know that that doesn't happen, right? You never get something for nothing. It always costs you. So when we move this to the right, and we increase the flux, which causes current to flow, that current flow decreases the flux, and we're fighting. In order to get more current to flow, what do we have to do? We have to push on this again, and we have to do work on this system in order to get electrical energy out. We have to put energy in. But it's important, if you listen to the words I used, I always said it opposes the change in flux. Sometimes it adds to it. It doesn't always subtract from the flux. So let's pretend we move the bar to the left. If we moved the bar to the left, you would think the current would go the other direction, right? Might be a guess you'd have, right? Well, let's see. We move the bar to the left, and the flux is getting less now into the board. So a current would get set up to add to it, to increase the flux, because it doesn't like change. As you move the bar to the left, the flux is being reduced because the area is being reduced. So a current would get set up in the clockwise direction to add flux back in to try to get it back to where it was. That's Lenz's law. Or we could look at the forces on the particles in this bar. As we move them to the left in a magnetic field, the positive would go down, the negative would go up. That's a current in the counterclockwise direction, exactly opposite of what we have when we move it to the right. So that kind of makes sense. If we move it to the right, we get one current. If we move it to the left, we get the opposite current. I think that makes sense. Forces, one way of looking at it. Lenz's law, another way. And if we wanted to quantify this, we could use Faraday's law. And that tells us that the EMF that's induced, we use the script E for EMF. That's the potential. It's the voltage. It's the potential that's generated. And I'm going to write it this way. the magnitude is the number of turns times the change in flux over the change in time. Like I said, if you're very careful with defining the direction of positive, negative flux and getting the delta flux, the right sign on that and the right sign everywhere, then the sign does tell you which way the current flows. But I think it's easier just to use Lenz's law or some other way to figure out the direction. But this gives you the ability to quantify it, which is nice. This puts a number in there. As we move the bar to the right at a certain speed, this tells us, oh, that acts like a 3-volt battery. If you double the speed, it acts like a 6-volt battery. We can put the numbers in and figure it out.